Good day. Today we're going to explore an amazing mathematical object called the Koch Snowflake. It's a beautiful example of a fractal, which is a shape that looks similar at different scales. Even if you zoom in infinitely, the structure still looks similar to the original shape. But don't worry, I'll keep it simple, and by the end of this talk, you'll be able to visualize and appreciate this fascinating object. So, what is the Koch Snowflake? The Koch Snowflake starts with a simple equilateral triangle and grows into an infinitely complex, snowflake-like shape. Each iteration adds more detail, making the perimeter infinitely long, but the area remains finite. Let me break this down step by step. First, start with an equilateral triangle. This will be the foundation of our snowflake. Next, divide each side into 3 equal parts. Now, take each of the 3 sides and divide them into 3 equal sections. At this stage, we have marked 2 points on each side, dividing it into thirds. Here's the interesting part. Take the middle third of each side and form an equilateral triangle that points outwards. Think of it as creating a little bump in the middle of each side. After doing this, remove the middle segment of the original triangle, the part where the new triangle sits. Now for the new shape that's formed, repeat the exact same steps. Divide every side into 3 parts, create smaller triangles and remove the middle parts. Do this again and again and again. Each time you repeat this process, the shape becomes more intricate with more and more points and angles. The figure starts resembling a snowflake with lots of small triangular protrusions. But there's a catch. Every time you do this, the perimeter of the snowflake gets longer and longer, approaching infinity. This means the snowflake's outline can go on forever. However, the area inside the snowflake never increases beyond a certain limit. Now let's talk about the key features of the Koch snowflake. First, we have the infinite perimeter. As we continue adding smaller and smaller triangles, the perimeter grows without bound. So even though the snowflake gets more detailed, you could never walk along the whole edge because it would take forever. Second, we have the finite area. Surprisingly, though the perimeter grows infinitely, the total area of the snowflake stabilizes at a fixed value. This happens because the added triangles get smaller and smaller, contributing less and less to the overall area. You can think of the Koch snowflake as a kind of idealized snowflake. In nature, snowflakes are fractals too, but they are not as perfect as the Koch snowflake. Real snowflakes also show intricate patterns, with each branch splitting into smaller branches as the snowflake grows. In fact, you can think of the Koch snowflake process as something similar to what happens in real-life fractals, just in a more controlled way. The Koch snowflake demonstrates a key concept in mathematics, infinity. It shows how a simple process can lead to something infinitely complex. Even though we keep adding smaller triangles, we are still working with just the basic idea of an equilateral triangle. This is a beautiful example of how simple rules can generate complex results, something that we see all over nature, from coastlines to mountain ranges, and even in the structure of plants and trees. In summary, the Koch snowflake is a perfect illustration of how an endlessly repeating process can create an infinitely detailed shape, even though the area remains bounded. It also shows us the concept of fractals, where the pattern looks the same no matter how much you zoom in. Whether it's in nature or mathematics, fractals like the Koch snowflake reveal a deeper structure and beauty in the world around us. I hope this explanation helped you understand the magic behind the Koch snowflake. It's a simple yet powerful concept that shows how infinity can emerge from the most basic ideas.